So I wanted to kind of talk about optimization because I wanted to uh, like cover what I forget what the course title is or something. Methods of Mathematical Modeling 3, something MA something something I forget. But so I wanted to cover first of all optimization. What is optimization? Because really I've actually properly forgotten uh, most of it. So this is an optimization problem in like its most general form, I think. So what we have is minimize some function subject to some that it is in some subject to that it's in some set, right? So this is the constraint on what the x can be, right? And so minimize what is called an objective function subject to some constraints, right? So this is a set of constraints. Okay, so this function, it is a function from Rn to R. So the reason we kind of want to use Rn and to R, well, because minimization wouldn't really work. Works best. Like for example, if you had a bunch of numbers, then to find the minimum, you would eventually have to turn it into a real number, right? Because you want to use the greater than or less than property. You can't take greater than or less than for like Rn. I mean, one way you could think about it is so you could take the norm on it to get the real, but you could do something more general as well for some other problem. You might need to do something more general for most problems. But anyway, we have this function from Rn, which you can use to represent most things, right? Most things that can be measured with numbers. Then you can put a bunch of numbers to measure a bunch of things. Okay, so that's basically what an optimization problem is in its general form. Something you also might need to know is what's called I've forgotten this name. What is it called? A feasible set, right? So sometimes we want to define what this is, a specific case, and the way we do it is we call it a feasible set, like this, with a fancy f. And the f is a set of a subset of the. So this omega is also a subset of the reals, right? Because that's where f is defined, a subset Rn. And if it's equal to Rn, which is also possible, then the problem is called unconstrained. But this f, this like this is, so it's elements in Rn, so it's a subset of Rn, but we have some constraints on it. So we have some equality constraints, right? Sorry, inequality constraints. So that just says it's less than some value. We want all of every we want all elements in x, so that g1 of x, for some functions, g1, g2 of x, all the way up to g something of x, say n, this is less than or equal to 0, and then we want some h1 of x, h2 of x, all the way up to hn of x equal to 0, and this is called equality constraints, right? And like, it's not really clear why you want, why you define it in such a weird way, but it turns out like whatever equality or whatever constraints you define by an equation, you can more or less write it like this, right? so if it's an equation depending just on this value x, so you just kind of have functions that so even if they don't depend on every single value of x, right? If there's g1, for example, if x is like x1 comma x2, then we could have g1 of x, right? If this is x, then we could have this just be x1 if we wanted, right? Or we could have it be like alternatively, we could have g2 of x equals x1 x2. It doesn't have to be linear or anything. We could also have another one, g3 of x equals x1 plus x2 or something else like that, right? Okay. And we just want all of these to be less than 0. Okay, so let's carry on. And so now we have a feasible set, right? And so so apparently if we find, suppose there is a, okay, first of all, suppose we're given this feasible set. Someone gives you some conditions and you found out the feasible set. Then you can now write the minimization problem. Minimize f of x subject to x is in this feasible set, right? And now let's suppose that f of x is bounded below on this set, right? So we can find an element, some real number, so that no matter what x you put in, right? So some real number c, such that whatever x you put in, f of x is bigger for all x in this feasible set. And that means that f has an infimum, right? It has a greatest lower bound, and so we can write that and we'll call that f star. So that's the smallest value f of x can take in this interval. So you can write that in notation like inf over this function of f of x, right? The smallest value can take in this set. Okay, and so that's fair enough. And unfortunately, this also has a name, right? And this is called the infimal value. I don't know if the names are actually important. I wonder if they'll just ask you, oh, find the infimal value, because I'll be fucked then. Oh, sorry, that's sorry. Anyway, and if you know, it's not necessary that this this exists, right? One way this could fail, right? Okay, for example, I said this condition, but another condition is for there to be an infimum, that f has to be non-empty, right? We have to have this and f is non-empty, and we need these two conditions because remember, for supremum to exist, we need it to be bounded, right, and non-empty. So it's the same for infimum. It's just like so supremum is bounded above, infimum is just bounded below. That's the only difference. And we also need it to be non-empty. So these two conditions mean that there's an infimal value, and then this infimal value is in the real numbers. So it's a bit weird to write it like this, but it's in the real numbers. In the case that f is empty, sorry, not f, it's called what do you call it? Feasible set is empty. Then we say that the problem is infeasible, right? If this f is empty, this optimization is infeasible. So if problem infeasible. Okay, and one last thing. If we okay, so we did one of the conditions, right? For infeasible, is if this condition fails. What about if this condition fails? Okay, we also have a name for that, right? If it turns out that it has no lower bound, if f if we range over this, we can't find a C that lower bounds f of x, then again this doesn't exist, the infimum value doesn't exist, and we say that the problem is unbounded, right? We say that f star, the least value f of x can take the minimum value is negative infinity, and the problem is unbounded. So this is if there exists C in R. This is if there does not exist C in R, such that C is less than f of, then we say this, and it's called unbounded. The problem is unbounded. Okay, so that's it for this first video. It's a bit long, but yeah, hope you understood what was going on.